I have a cosine theta. Dx is z secant squared theta d theta. And r squared is z squared secant squared theta. Right? And all of this is out of the board. So notice that this is kind of nice because the secant squared cancels. And also one of these z's cancels, right? And z is a fixed quantity. You know, we're just looking at a fixed distance above the midpoint. So that's a quantity. So that's fixed. So B equals, I'll just say out of the board. And then mu naught I over 4 pi z. And then I have the integral of the cosine of theta d theta, which isn't a bad integral to solve. So that turned out to be a good change of variables.
We can take z out because it's a constant, right?
Yeah.
Okay.
Did I not take it out?
No, you did. I was just making sure.
Yes, because z is a constant. Now, this is an integral with respect to theta. So I'm integrating with respect to this theta over here. And theta is like, is like this, right? Actually, on this line, the way that I defined it, theta is equal to 0. Okay? So I have to do the integral so that I include the contribution to the magnetic field here from all the dx's, all the current in this segment. So I actually have to integrate from, maybe I'll use green now. I have to integrate from, from this value of theta, right? And then the next theta, and then all the way out to this. And because we are above the midpoint, the contribution from this side, this half, is going to be equal to the contribution from that half. So I could call it, I could just integrate from theta equals 0 to theta equals this value here, which would be like, this would be like theta max, right? And then multiply by 2. Or I can do it from this here, which is minus theta max, to theta max. Either way. So I could do it like this. I could say that I'm integrating from theta equals minus theta max to theta equals plus theta max. Or I could say it's out of the board and then say mu naught I over 4 pi z, and then do the integral from theta equals 0 to theta max. But multiply by 2. So what do you prefer?
2 times.
Either one is
The second one.
right? If not, I mean, you could actually express it in a couple of ways. I mean, you could say from theta equals theta 1 to theta equals theta 2, where theta 1 and theta 2 are given by those values. Or you could just use this. Right? So, well, this would be more general. This would be more general if this point were not at the top. Suppose this point here that we're calculating the magnetic field at, suppose we have the line segment like this, right? So this is, all of this is 2L. And suppose the point is over here. All right, so this distance is Z. Then this angle here would be theta 1, and this angle here would be theta 2. So if I use, from theta 1 to theta 2, like some angles like this, then that would be an expression that would be more general without putting in theta max and minus theta max. But since we are above the midpoint, Then I could use theta 1 is minus theta max and theta 2 is plus theta max, or from symmetry, integrate from 0 to theta max and then multiply by 2. So if we were doing it about some other point, this is the current I, that's at a distance z from the wire over here where the current is at, then the more general expression would be this. It would be out of the board, and then it would be mu naught I 4 pi z, and the integral of that will be from sine of theta max, or theta 2 minus the sine of theta 1. That's, that would be a more general expression. Now, specifically to this problem, with this point being above the midpoint, then this becomes, then it's either, I can either put minus theta max or plus theta max, or from 0 to theta max, and that would just, it's easier to do it like this. This would be out of the board, and it would be mu naught I over 2 pi z, and that would be the sine of theta max. Now, theta max was not given in the problem. So what is theta max? In fact, what is the sine of theta max? It will be, well, this is theta max over here, right? So, and this length over here is the square root of z squared plus L squared, correct? Right? Because this is L. Yes or no? And the sine of this angle, if you look at this triangle, if you look at this triangle, the sine of this angle is the opposite side, which is L divided by that. Anyway, I have to erase some of this because I run out of board, and I'll just erase this part over here. So the answer is mu naught I over 2 pi z, and then this is L over the square root of z squared plus L squared. This is the answer to the problem. Now, in the textbook, this is an example that's worked out, and what they did in the textbook is they put the line segment vertical, and they call the distance from the midpoint, they call it x. And I think they said that this is like, this is A and this is A, so the whole length is 2A. And the current is probably this way. Right? And so there is an expression that's, that they came up with in the textbook, in that example that they solved in this chapter. So if you look in my notes for chapter 28, I wrote down only the answer. I didn't want to do that calculation. So this is what they did. So they used a figure like this. So yes, they call the length of this thing 2A. So this is like y, this is 0, this is y equals minus A, y equals plus A. And the question is find the magnetic field over there. This is x from the midpoint. And the result, they did this problem, right? And in the textbook, right, the author did it, and then you apply, and the result is this. Which we have what? We have mu naught I, and then here they have 2a over 4 pi, which would really be the length or half the length of the wire. That 2 and this 4 will give you a 2 pi downstairs, which is what we have over here. Then x is the distance from the midpoint to the, of the wire to where they're finding the magnetic field, and then x squared plus half of the whole length, which is L. So, this is, that answer is the same as this answer. Right. Except that they call this X, they call the L A, and then they call this X, this is A. I thought it would be easier to see it if the line segment is horizontal rather than the way it was done in the textbook, vertical. I just thought it would be easier. But, they are equivalent ways. But this is probably the most complicated example that you can do, where you do an integral. It's a finite straight line segment, and you have to use the Biot-Savart law. And it involves a cross product. We dealt with the cross product over here, right? If you know the rules of how to calculate a cross product, then it's no big deal. At some point, you get to an integral with 3 variables. And before you evaluate the integral, you have to express, the integrand in terms of 1 variable and constants, and then do the integral. Right? And for me, I decided to express x and, what was the other? X and r in terms of theta, and doing that, you end up with a very simple integral to solve. And then you put in the limits of integration, but then we have to express the answer in terms of the given quantities, not in terms of what we introduced, right? Like the theta max, that's the name that I gave it, right? So don't express your answer in terms of something that wasn't given. So find the relationship between this quantity and theta max and what was actually given in the problem. And so it's this, and you get this result. So when we were learning about calculations of electric fields back in chapter 21, we did something similar with Coulomb's law, k dq of r squared, and we did some integrals, and then we moved on and we learned about Gauss's law, which is a very powerful technique for very quickly figuring out, calculating the electric field generated by charge distributions over extended objects with certain symmetries. Right? If we had point charges, we could use Gauss's law. If we had an infinitely long wire, we could use Gauss's law. If we had a sphere with charge distributed maybe uniformly, and only if it has a rate of dependence, we could still use Gauss's law. And if we had an infinitely large sheet, we could use Gauss's law, right? And that was it, pretty much. And we did cases of conducting materials in electrostatic equilibrium and dielectric materials, and we did that, right? So there is a technique similar to Gauss's law for the case of magnetism. Again, in just a couple of lines, you can come up with an expression for the magnetic field generated by by certain current distributions, where the current is constant, but it only in certain geometries is it practical to apply this technique, which is similar to Gauss's law. But before I do that, that technique is known as Ampere's law. But before I talk about that, how about I take a limit over here? What happens if the wire, if this segment of wire over here with constant current I in it, what if this is very, very, very long, like infinitely long that way and infinitely long this way? What would happen if that's the case? So let me just consider that limit. In other words, you're looking at a line segment, right? And then you're so close to it that this end looks like very, very, very far away. I mean, this distance is very big compared to this little distance. In other words, what if you take the limit as L is much greater than Z, or Z is much less than L? So what if, let's say Z is much less than the length of the wire? So what happens over here? Well, if Z is much less than that, then this square root of Z squared plus L squared will become, well, L is big and it gets squared, so it's very big compared to Z squared, so this just approximates to L squared. It's like, this is 0, so this is just L, right? And in that limit, this magnetic field becomes mu naught I over 2 pi Z, and then we have an L in the numerator, and that square root in the denominator just becomes an L, which cancels that. And this is out of the board, right? So therefore, B net equals mu naught I over 2 pi, and Z, right? So what we are going to do with Ampere's law is we are going to consider a wire that is infinitely long, and not just, there's no such thing as a wire that is infinitely long, but a wire that's very long compared to how far away from the wire you're calculating the magnetic field. And what we're going to do is we're going to do a problem like this, where we're going to say this is infinitely long, the current in it is I, and we want to know what is the magnetic field. Well, that's just like a wire that's straight, and we just want to know what is the magnetic field at some distance R. Usually we just talk about this distance being R away from the wire, and we'll find that with Ampere's law, the magnetic field over there will be mu naught I over 2 pi R out. Which is this result, with Z being replaced by R. It's exactly the same result. Except that you saw how it took me a little while to get to this answer and then take the limit. Whereas with Ampere's law, a couple of lines, and we're going to get it just like Gauss's law, right? What we do here is we imagine not a closed surface, but we imagine a closed loop. So the closed loop that we imagine in this case is going to be a ring. So this is it's called an Amperian loop. So Ampere's law is this, where you imagine a ring or a loop, which is called the Amperian loop. In Gauss's law, we imagine a closed surface, and we call it the Gaussian surface. Actually, this is easier because instead of thinking of, in 3 dimensions like a surface that's closed, this is just a loop, right? And the loops that we are going to imagine are going to be on a plane. So this turns out to be just, and then this is just, again, this mu naught plays the role of 1 over epsilon naught in Gauss's law. And then I enclose is the total current that goes through the loop that you imagine. And this just becomes, at this point you just write B, and then the L becomes the length of the Amperian loop, which is a circle, so it's 2 pi R, and this is mu naught. And what is the total current that goes through that loop? It's just the current in the wire I. And then the next line is the answer. This is Ampere's law, which is given. This is what we put in the problem. And the answer, this is just algebra, right? And this here is given. So all you need to do is write something like this, and in the next line, you have an answer. I mean, that's a lot quicker than having to do the problem like I did over here. Right, where I had variables, and I had to find relationships between them. I had to remember a trig identity. I had to remember that the derivative of the tangent is the secant squared, and I had to remember that 1 plus tangent squared is the secant squared, right? So it's just a lot to remember there. Whereas with Ampere's law, boom, a line or two and you're done. So this is what I like to talk about next. I like to talk about this other technique for calculating magnetic fields generated by constant current, but again, it's practical only in some cases. Like Gauss's law was only practical in some cases. Ampere's law is only practical in some cases. Right? And in the case of Gauss's law, we imagined a closed Gaussian surface. Here, in Ampere's law, we imagine a closed loop, not a surface, but a loop is what we imagine. And then in Gauss's law, we were interested in the total charge enclosed by that Gaussian surface that we imagined. And here, what we calculate, or what we consider, is the total current enclosed by the loop, the total current going through the loop.
But the loop is infinitely thin?
No, the loop is going to be finite.
No, like so if it's enclosed, it's thin, right? Like it,
No, it's a loop, so I imagine a ring. A ring. That's a loop. And I just want the total current that goes through it. And sometimes you're going to have current going this way and current going the other way, and you got to take the difference between them. Just like in Gauss's law, you might have had positive charges and negative charges enclosed, and it's the sum of them will, tend to cancel them out. So let me talk about Ampere's law and then do various examples. There are only some examples that can be done, really. You'll see that because of your experience with Gauss's law, you'll see that this is actually, I think, simpler. I hope you find a little simpler. So this is the ring problem that we did last week. So I did this in detail. In fact, we did a segment of it. So here's Ampere's law, right? So that just says when he lived. So this guy was born, 1 year before, he was 1 year old when the US declared its independence from Britain. So Ampere's law is that. So you consider an integral. The circle that you see in the integral sign just means that you have a closed, but this is actually a line integral. It's a closed loop. In Gauss's law, we had E dot dA. It was a surface integral, so it was a closed surface. But this is B dot dL, so this is a closed loop that we consider. And just like in Gauss's law, we had the electric field dotted. The electric field at the Gaussian surface dotted, the dot product, with the area vector of the Gaussian surface. Now we consider the dot product between the magnetic field at the Amperian loop, dotted with an infinitesimal length along the Amperian loop. And that integral is related to the total current that is enclosed, that goes through the loop that we imagine. So I guess I wrote it in this here. So here we imagine a loop. B in this expression is the magnetic field at the Amperian loop. The name of that loop that you imagine is the Amperian loop, just like in Gauss's law. The surface, the closed surface that you imagine was a Gaussian surface. This is called an Amperian loop. So B is the magnetic field at the Amperian loop. Right. This, I wrote it the S over here, but it's the same as that one, the L. I guess I should have been consistent, and I should have called this the S, but it's just an infinitesimal length along the loop that you imagine, and I enclose is just the net current that goes through the loop. So, applications. So see examples. Well, that's for me. Look at the extra examples. I'm going to go here and look for those examples on chapter 28. Here we go. So it's number 3. Because we did extra example number 1, we did number 2 now, today. And now I'll just like to do, you know, a series of these guys. Let me, just to facilitate this, make it easier, let me just get a ring that's bigger so it's easier for you to see. I'll be right back.